Hello, everyone, and thank you for joining today's webinar. My name is Richard Alberger, and I'm a Partner Solutions Architect in IoT at Amazon Web Services, and I'm excited to have the opportunity to speak with you today about machine learning at the edge. Let's get started. First, we're going through a high-level overview of the machine learning at the edge landscape. And then next, we're going to talk through 4 tenets of what our customers look for when doing machine learning at the edge. Then we'll look at a generalized industrial IoT architecture. The architecture reflects how data typically inflows and outflows with our industrial customers that are using IoT Core. Then we'll go through a 4-part story specifically referencing how machine learning at the edge works with our partner Xilinx. Let's get started with the overview now. It's been going on since the Industrial Revolution. We build machines to work on our behalf to make our lives better. And as we make devices smarter, the next natural progression is to have these machines detect things that happen in our environment, such as a room getting brighter or hotter, or even having different chemical compositions in the air, such as carbon monoxide. And if we detect that a room is getting warmer, maybe due to outdoor temperature, we may want a device like a thermostat automatically gauge the temperature setting to keep the room comfortable. This might be due to the number of humans in the room or the floor beneath getting warmer or similar other actions. Then when we want the device to make a decision about what we're estimating or inferring about that environment, we want to act on those decisions or those inferences. So if we're a cloud company, why don't we ask people to build that smartness in the AWS Cloud and just do web API calls to interact with that smartness? Well, when speaking with customers, we discovered that there's 4 reasons why we operate machine learning at the edge. First is latency. Even with the fastest network possible, actuation may not occur quickly enough. The next is bandwidth. When machines at the edge can generate tremendous amount of information, we may want to use all that information to make great inferences. We can't physically transmit all that data to the cloud to make the same decisions. The next is availability. The machine needs to operate even when the network goes down. So these machines performing the inference need to be self-sufficient. And then there's privacy. There's laws about data sovereignty and perhaps also personal information that organizations can't put into the cloud that is regulated by provisions in HIPAA, for example. Where can these apply? Let's go take a look. Although machine learning at the edge operates in many use cases, let's look at a few here. The first is predictive maintenance. Take the HVAC in your home, for example. Predictive maintenance can be used to determine not only if the integrity of the coil in the HVAC is degrading, but also when it will degrade and become absolutely critical. The next is robotics. On manufacturing lines, robotics can be in the same area as humans. We can use machine learning to detect if there are foreign objects in the operating area and to cease operation in that case. For example, if a human walks into an operating area, we don't want the robot to harm the human, right? That also relates to the image recognition case at a more specific, tangible level. And then there's agriculture. It's not just about soil moisture. Machine learning is used to determine the correct calibration of chemicals and the amount of fertilizers that you would use in that case based on current state analysis of the farm. So let's move on forward to tenets and reference cases. The first tenet is to effectively maintain the system over its life cycle. To fulfill this tenet, there are 3 main points we need to cover off. The first is to make upgrade and support optimizations. The next is achieving deployment efficiencies, and that includes security-related patching. Then, when we need to ensure that we implement the right mechanisms to minimize system downtime. AWS provides this capability to customers through AWS IoT device management. When we're building systems with model-based calibration and model predictive control, we want to improve those systems over time to generate increasing levels of value. We need to retrieve data from the environment through inputs such as sound sensors, electromechanical sensors, and video, for example. By retrieving that data and propagating it to the AWS Cloud, we can extend the life and usefulness of devices through real-time maintenance and better predictions. This is the tenet we're focused on today throughout the rest of the talk, which is facilitated by AWS IoT Greengrass machine learning. Although raising alarms and having pretty visualizations might be nice, the real value of aggregating logs and visualization is making the data actionable. Right now, customers are asking how they can derive both short-term and long-term value. Short-term doesn't mean low value, and many times it can be safety critical value like dispatching emergency teams. Long-term value is around identifying trends, not only in weeks or months, but in years. Customers have been using services such as CloudWatch and AWS partner solutions to monitor system health from local and global levels. And then finally, we want to be able to drive value through new opportunities. And how do we take all this work we're doing to make cool stuff happen and derive even more value from it? From a partner perspective, we want to help our customers have a better experience. This means taking the functionality we're building on a case-by-case basis, abstracting and reselling. Now, lots of companies do this today with partners like Xilinx by selling what's called IP blocks. Customers license the IP and then apply it to the FPGA. Looking forward, we can take similar vein and apply that to the connectors world where we've only scratched the surface. So let's take a look at a natural gas use case here. Let's go ahead and focus on the component areas of the system. The main housing unit houses the AWS IoT Greengrass instance. Why is that? We're not only going to use it from an architecture perspective as an aggregator for all the other components in the window, but we're also going to make it responsible for object classification to detect if humans inside the housing unit should be there or not. Of course, this system will need to handle safety and non-safety critical aspects of the overall design. Then all around the central function are devices that must run in a deterministic fashion. Some may be battery controlled, some may not. For example, the backup generators may be triggered by a signal in the main compressor housing that the main power has failed, and the device to do that is very small and specific to function. We'll be focusing on these two components of the system for the understanding of the connection between AWS IoT Greengrass, Amazon FreeRTOS, and the AWS Cloud later on in this talk. So I want to take a look at another angle from an industrial architecture perspective. We really looked at the edge side, but to give you a fuller picture, I want to also take a look at what we're doing with that data up in the AWS Cloud. So on the edge, all the smartness on the edge that's happening there, what's happening is we have industrial controlled field bus units within an industrial ecosystem feeding data to AWS IoT Greengrass. And as part of AWS IoT Greengrass, we have Lambda functions, and those Lambda functions can do protocol translation, and they can also invoke models, which is the machine learning part of the process. So we can go and do inferencing, for example, if we want to do predictive maintenance, or if we want to take a look at if there's some other object issue in the ecosystem, we can go and invoke that model and make an inference or a guess on whether or not there needs to be done, something needs to be done. But that's not the end game. What we want to be able to do is take that data and do something useful with it. And there's a few different things that we can do with that data. By facilitating that data up to AWS IoT Core, we can then proxy that data into different kinds of data sets for different purposes. Now, what's also interesting about AWS IoT Core is that we can fan out data into multiple different services for different purposes. So in this particular case, we're fanning out to Kinesis data streams, Kinesis data firehose, and AWS IoT analytics, all for different purposes. So let's take a look at the top case. In the top case, what we're doing is analytics in a pipeline sense to determine if there is an issue with a particular item in the ecosystem that we happen to be monitoring. Now, this could be done with analytics in the context of long-term analytics, right? And then we can push this through Amazon Athena and then visualize that in QuickSight, right? In the next case, what we can do is fire hose that data directly into an S3 bucket, which can be the seeding point for our data lake. The data lake is going to be the source point of our data that's going to feed into building the machine learning models. We're going to be talking about that in a lot more detail later. But we can also look at that data lake data and slice and dice it using Athena and then visualize that again in QuickSight. Now, what we can do at this point is pull in multiple sources of data depending on how you're curating that data into SageMaker. SageMaker is a platform that you use to organize your data, to build your machine learning model, to test your machine learning model, and then stage your model for delivery to the edge. So on the left-hand side of Amazon SageMaker, what we'll be talking about later on today in more detail is how that artifact is actually staged into S3, and then how AWS IoT Greengrass is used to deliver that model from the cloud down to the edge so we can get this full cycle of taking the data that you're generating from the edge, putting it up into the cloud, generating new intelligence, and then bringing that back down to the edge and having it feed on itself. But I also wanted to demonstrate here that the data doesn't only have to be used for machine learning, you can also use it for analytics and other purposes. So let's go forward and take a look in more detail about the machine learning lifecycle. Now, AWS provides a lot of services here for you to curate this entire lifecycle. And I'm going to start off in the lower left-hand corner because we always have to start with the data. The data is the root of everything. In order to, we won't be able to build a machine learning model unless we have the data. So we need to take some fundamental data and bring that up into the cloud. In the lower left-hand corner, we need to take the data and then facilitate it through some entryway, through some ingest point. Now, once that data is ingested, we're going to bring it up into the upper left-hand quadrant, and we're going to curate that data into one of these services. We'll be talking about these services later in this talk. And then, once that data is curated into a curated data lake, then we can move on to the upper right-hand quadrant and understand how we can take the data that we've curated and build an effective machine learning model based on an algorithm that fits your particular purpose. And once that algorithm is built, then you can stage it and you can deliver it to one of the systems in the lower right-hand corner. So the main system that we'll be talking about today is AWS IoT Greengrass and how Greengrass facilitates the invocation of those inferences. Specifically to Xilinx, in the upper right-hand corner, what you would use is the Xilinx Deep Neural Network Development Kit. And then you use that to build your model. We can stage that and then deliver that down to the edge into one of these two components, because the model that is generated from the DNNDK is a bit stream that actually gets applied to your FPGA, and that's the accelerator part of the hardware. So let's go forward onto the next section and understand, well, that lower left-hand quadrant, what do we need to do to feed that data lake? How can we use IoT Core or Kinesis or AWS Snowball or even Snowmobile to bring data up into the AWS cloud? Because in the beginning, you have nothing, right? In the beginning, you don't have a data lake and you need to seed that data. To get started, how do you get started with a sample data set? How do you generate your own data? We need to teach the computer eventually how to make predictions. And that's pure math, which means we need data and lots of it to have any degree of accuracy to, well, from a statistical perspective, be reputable. Sure, there are a lot of out-of-the-box algorithms to help you, but you need to feed the algorithm data crunching monster, right? So you can sometimes seed this data with your documentation that comes with the component that you happen to be monitoring, for example, in your data sheet, but that's going to give you laboratory conditions. So you'll also need to feed it with other data that is for your own operating conditions. So there's a few um, different ingest points based on the type of situation that you're working in. And let's take this step by step. Now, if you're in the Internet of Things and you have a singular device that's connected directly to IoT Core, and you have hundreds of thousands or millions of these devices operating and you're pushing MQTT telemetry to IoT Core, what you'll want to do is eventually get that into your data lake, and you can use Kinesis Firehose to facilitate that data. In the next case, you may have large amounts of video data, and it may be a little bit challenging to facilitate that video data up through IoT Core. So we would use Kinesis video streams in order to facilitate that data directly to S3. Now, if you're in an offline situation where you can't get a large amount of data and you want to, say, capture all your information from your aircraft throughout a flight and then use that for your analytics data, then you'll need to put that on a data set that's offline, such as Snowball. And then once you get back on the ground, you can send your Snowball to AWS and we'll put that data into S3. That's how you can quickly get a large amount of data ingested for your machine learning algorithm. And then finally, what you can do is if you don't want to route directly to Kinesis Firehose and in your particular solution, you have DynamoDB, then you can always push that data to IoT Core, send it to DynamoDB, and then use DynamoDB streams to feed your data lake as well. So let's talk about how we're going to curate that data lake actually after you get that raw data into S3. You don't want to taint your raw data because that is your golden data set. So what we want to be able to do is take that golden data set and actually curate that data into another S3 bucket, right? So you have stages of curation, so you don't taint your original data set. So let's see how we do that with the services in the upper left-hand corner using IoT analytics, storing it in S3, maybe doing some labeling by leveraging SageMaker Ground Truth, and using Amazon EMR for mass scale slicing and dicing of data. So we can use one of these services to actually take your golden data set and evolve it into a curated data set. Now, AWS IoT Analytics gives you virtually a one-stop shop. It manages data sets for you. And you can use those data sets directly to ingest into SageMaker when you're building your machine learning algorithm. You can also take data, like when you're prototyping, directly from your raw data set and facilitate that using a SageMaker notebook, right? But when you're really dealing with things at scale, you may want to take a look at EMR, especially when you're talking about textual information, because you'll need to slice and dice gigs or terabytes or zettabytes or even more of data, slicing and dicing that original data set based on your need, and then putting that into another bucket. But that's, again, not the last thing for you to do, because this is really an art form. Identifying the right set of algorithms to apply to the right data sets, categorizing the data properly, cleansing the data properly, identifying the right data types that you want to use for the actual target algorithm is really still an art form in the industry. So we want to take those data sets from S3 and also IoT Analytics. Have your SageMaker notebook facilitate that. You can annotate and cleanse and identify your data types, but you're going to build these models over and over again. You can quickly iterate on the testing of your algorithms against data sets using SageMaker and SageMaker endpoints, using testing endpoints. So let's take a look at model training and staging at that point. We now have figured out what the data set should look like, or we have a first snapshot of it, and we can iterate between building the model and cleansing the data. But let's take a look at that next step, which is model training and then getting that model staged. And that's actually the upper right-hand corner. And we could be using one of these tools or compilers to facilitate that. We could be using MXNet or some other compiler for that. We could be using the deep learning AMIs that have the tool chains already installed, using SageMaker and the containers that compose the tools for SageMaker to facilitate that, and be using EC2 P3 instances to build those models. So when you look at the entire landscape of the machine learning tool chains that AWS has to offer, you can think of it as a stack that actually helps you identify accessibility of tool chains. So if you're not very familiar with machine learning and you just want to get started, you want to see some results or how you may be able, or you want to use machine learning, you'll be looking at the top layer of this, right? There's a finite set of cases that you would apply using these services. And then from that, either those services suit your needs, which they very well could, or you need to do something deeper. And we're working with customers in both of those cases. But today, what we're focused on is actually these two lower layers, which is maybe you have a more unique case and you want to actually do the machine learning at the edge, and then so you need to actually build that model yourself. You can't use a managed service to do that and facilitate the model delivery down to the edge. So let's take a look at what that looks like from a tool chain perspective. Now, there's the tool chain on the left-hand side, the MXNet or the PyTorch or the TensorFlow. This is what developers will use to develop their algorithm. What data set they want to use, what algorithms they want to use, how the data set loads, any other computations they want to perform on the data before it gets loaded into the algorithm to do the work on the P3 instance to actually output the model. Under the covers, though, if you're using SageMaker, what you're not necessarily aware of is the lower level compiler to actually build the model, which is in the middle there. So you're doing your Python programming, for example, and you're defining your algorithm, and you say, okay, I want to actually build my model now. And it does some magic. It launches an instance to build your model, but what it actually knows is, well, what compiler toolchain do I need to use? And actually facilitates the transfer of that toolchain onto the instance and builds the model for you. So it removes a lot of the complexity of you having to learn the low-level details of these machine learning compilers. So let's take a look at what that looks like when we want to actually feed the art. When we want to bring the data sets on the right-hand side that we've defined within S3 and also IoT analytics, and how we take the work we've done into SageMaker on the left-hand side and put that into some compute in order to feed this art form that you've defined so you can predict outcomes. On the left-hand side, you're going to bring in your notebook. This is the computational instruction that you've developed to define what you want to predict and how you want to predict it. In the middle, you have a compute component. And what is used most commonly today is a P3 instance to actually compute these machine learning algorithms. And on the right-hand side, you'll have your bespoke curated data lake in S3 or a more regimented defined data set, which would be an AWS IoT Analytics. And you can feed all these data sets together into your P3 instance and compute it. And AWS provides all the heavy lifting in SageMaker to facilitate that. Now, it's going to bring in this model compiler into the P3 instance, which is actually composed within a container, puts it onto the P3 instance, and then does the compute on the algorithm against those data sets. And eventually it outputs a machine learning model, which is represented on the bottom of the slide. Now, what we need to do now is we need to get that model down to the edge, right? So we've gone from the notebook to the P3 instance to generating the model, and we're going to take that model and SageMaker puts it on an S3 bucket for us. Okay, so now that model, which is a binary blob represented by a binary blob is now sitting on an S3 bucket that we can take and do something effective with it, right? So now what we want to do is take that model and put it down the edge. Actually, this next section splits it into a couple of different pieces. One piece is, what does it mean to take that model, put it onto a machine at the edge, and then using acceleration at the edge to facilitate the invocation of that model. And the second part of this is the mechanics around getting the model from the cloud down to the edge. So that's the lower left-hand piece. And we're going to be focused specifically on AWS IoT Greengrass. Now in this, in that for IoT Greengrass, when we're talking about the Xilinx case in the FPGA, we're actually using what we see in the upper left-hand corner is the A53, Cortex A53, which is the system or the cores where Linux runs. And then what we also have on the lower hand is the programmable logic. Now, what I'm going to do now is go through each of these steps, so these blocks one by one, and explain them to you. And actually, I'm just joking. Those are for the rest of this talk, all we really care about is the processing system and the programmable logic. The processing system is where Linux runs and AWS IoT Greengrass runs on top of that. The programmable logic is the FPGA fabric that is going to be doing the accelerated inferencing. So how exactly does that work? It looks like we have two different CPUs. How do they talk? The lower is not really a CPU, but how do these two components talk to one another? Well, let's take a look at that mixed criticality system and how we actually place that software. On the left hand, we have that Cortex A53 processor that we just talked about. That's called a programmable system. And we can run operating systems like Ubuntu or Debian on that. But today, what most of the customers are running is either Pentalytics, which is a curated version of Yocto by Xilinx, or just Yocto on the left-hand side. And today, what AWS has is a meta AWS layer, bake layer, that enables you to quickly and easily get Greengrass onto your system. On the right-hand side, we have the programmable logic, which is the FPGA side. And use a tool in Xilinx speak called Vivado to define what your logic is, and then it creates a bit stream. So now you can kind of see, oh, if Vivado is creating the bit stream, then what am I doing for using the DNN-DK? Virtually the same thing. We're building the machine learning model and we're putting it onto the programmable logic to accelerate the invocation of the inference. So how does it talk to actual hardware? Well, if you look at the back of the chip, you have all these pins, right? Well, you know that Linux is a non-deterministic system. And we want to be able to do inference, especially with video, using deterministic systems, right? We want the video to be super fast and we don't want a lot of other system processes to get in the way. So what we would do is actually take the camera to do, like, for example, object classification, and wire that up directly to the pins and talk directly to the programmable logic side. So we can do inferencing directly. That is really accelerating the invocation. So what we want to do then is, once that model is in S3, we can move that model down to Greengrass by using the machine learning component of AWS IoT Greengrass. The configuration enables you to take the machine learning model that we put in the S3 bucket and do some very easy to use configuration to take it on an iterative basis and then deploy that down to the edge. And all those mechanics that you usually have to put together in order to copy files from the cloud to the edge is all baked into the machine learning component for AWS IoT Greengrass. So once we've transferred that model from the cloud down to the edge, let's talk about how that actually starts getting invoked down at the edge. Now, when we're using AWS IoT Greengrass, we'll be using a Lambda function to facilitate that invocation. In this particular case, it's going to invoke a SDK that's on the local machine, and by invoking the model from the local machine, what it's going to do is actually talk through some shared memory in order to talk to those logic gates down at the bottom. Those logic gates at the bottom, that actually represents the FPGA bit stream that we applied. That actually represents the machine learning model that we developed and we built and compiled and transferred down to the edge to actually do the inference work. And once you start doing the inference work, then you'll start getting results. Now, say, for example, we're trying to take a look at an inference that we find a human being in that compressor house that we talked about earlier in the talk. And if we see a person, we want to start loading images onto the local machine, right? Because eventually what we want to do is alert someone that there's someone in that compressor house, right? So we're actually taking the video feed that's going into the FPGA, it's doing the inference work, and then shooting back out through shared memory the images that it's capturing with the person that the machine learning model detected. Now, that's all good and fine. We have a bunch of images on that local machine, but we still haven't notified anyone on how on those inferences. Now, one thing to note here, when we're talking between these two different channels, what we want to be able to do is talk directly to the hardware on the other side. And I want to note here that AWS IoT Greengrass provides a lot of protections that make it so you have the lowest footprint or on the system, right? You have the lowest security profile on the system to run your applications by default. In order to do this kind of invocation, you do need to open up certain devices on the Linux system that are named on the left-hand side in order to interoperate with the FPGA in this case. So Greengrass has all those protections for that kind of invocation configuration already built into it. So it's really, the top are more common, and on the lower half, that's the shared memory that I was talking about, how those images get transferred back from the FPGA down to the programmable system side, to the Linux side. So now we want to take those images and notify someone about that, right? We want to actually get that back up into the cloud, that we actually saw we saw something that was classified. So the way that we usually do that is that we would use a feature that's built directly into IoT Greengrass called the Token Exchange Service, or TES. Token Exchange Service, based on the IoT core communication that you already established by running Greengrass, it can get an STS token from the cloud and use that STS token to communicate with any service in the cloud that you want it to communicate to, and that's governed through roles that are applied to the Greengrass core instance. Now you might ask, well, how do I know that images are actually being applied to the system? Well, you can just implement a simple watchdog mechanism in AWS Lambda, because Lambda on Greengrass that's running on hardware that you own and operate has the ability to listen to file system events. So once you hear that a new image has arrived, you can pick up that image and then copy it to S3. And then from there, you can do lots of other things, such as throwing an S3 event to Lambda function to actually do some more interesting work with that image, such as doing a notification like what we talked about when we were looking at the industrial IoT architecture slide, that top slice of the channel that we looked at. So then what we're thinking is, well, we may want to do that for alerting situations when we know that something has gone wrong. But what if we just want to acquire more data to build up the data lake so we can make our algorithms smarter? Well, what we can do is take other images, well, maybe just snapshot images of the system to actually gather that data and maybe say, for example, if a coyote happened to be running by the building where the compressor is, and the machine learning model saw something move, but it didn't know exactly what it was, we can use that kind of common object classification as a negative case in our machine learning model. So how would we gather up all those images? Well, we wouldn't want to constantly funnel that data up into the cloud to S3 just to classify it, because it could be taking up too much bandwidth. So we could use a component such as Snowball to store all that data images and then take those data images and send them to AWS so you can again build up your data lake. So you can start to see that it's all about the machine learning cycle, right? Bringing all that data that you're generating down at the edge and then enriching it up in the cloud to have better intelligent outcomes. So let's take a recap of the situation that we just went through. At the beginning of this 4-part talk that we talked about the data transport. How do we ingest that data up into the cloud? We can do it in near real time, which is with AWS IoT Core, and then facilitating other kinds of data through Kinesis, like Kinesis video streams, for example. Or we can do that in offline data keys, such as using Snowball or even Snowmobile to transfer your data from the edge up into the AWS Cloud. Once that data is in the AWS Cloud, you want to curate that data. I want you to keep in mind that you always want to keep your golden data set. Don't taint your golden data set. And from your golden data set, you can create tiers of curated data. And that enables you to always go back to the original data set if you have different purposes or reuse for that data. Also remember that AWS IoT Analytics is super great in curating data sets, especially when you have upfront identifiable cases, right? So you can ingest that directly into IoT Analytics from AWS IoT Core. If you want to enrich a data lake at scale, and then you want to curate that data, always keep in mind Amazon EMR or Elastic MapReduce to actually slice and dice your data at scale. Once it's sliced and diced, it goes into another S3 bucket. Don't taint your original bucket. Once that's been done, then again, you can take your Amazon SageMaker to define your algorithms, use the P3 instances for the compute to compile your models, and then you stage those models in S3 so you can actually improve the intelligence on those devices down at the edge, right? We want to make this a cycle. We want to extend the lifespan of those devices that you're deploying down at the edge. We want to make them smarter over time. That's how you derive the real value from machine learning at the edge. So with that, my name is Richard Elberger. I'm a solutions architect in IoT at Amazon Web Services. This is my contact information. From there, what you can also see is the Meta AWS project, which is in the AWS organization for more information about building Yocto and including Greengrass and machine learning and SageMaker Neo. And I think it's time to do some Q&A.